This video should cover how to get the power supply to create the rail voltages you need, and how to get the data sheet for the op amp that you have. So if you're asked to set up this sort of circuit, this is a non-inverting amplifier circuit using an op amp. We're asked to sweep the input voltage from 0 to 3, show the input versus output voltage. We see that VDD is listed as +3, VSS is going to be -3 volts. We have 2 resistors, an input voltage, a ground node. So what we're going to try to do is set up this power supply to provide the voltages that we need to set up an op amp. So if we don't know what op amp we have, we can look at our integrated circuit here. I don't know if I can, there you go, MCP6002. Can't really get that very clear on the camera. There we go. MCP6002. So if you don't have the data sheet to show the pin out, what each pin does, it's a little diagram showing what each pin of your op amp chip can do, then you can easily just Google data sheets for devices that you have. Let's look at this first link here, open a new tab. There you go, MCP6002. Status in production. That's good. Download datasheet. So let's click that. Opens a new tab. MCP6001, R1R, 1U, 2, and 4. Those are different types of packages, different types of devices that all use the same sort of underlying 1 megahertz low power op amp that we have here. You can notice that this is a 50-page PDF. So this is a data sheet. This is the sheet of paper with all of the data. And it has everything that you might need to construct an op amp circuit or use this type of device. So if we're looking at the MCP6002 here, notice we have 2 op amps on a single chip. They share the same VSS and VDD. VDD is our positive and VSS will be our negative supply voltages. If your circuit only calls for a single op amp, you can just use one side or the other. Or if you want to use one op amp for one circuit, another op amp for a different circuit, feel free. But it's just 2 op amps housed on the same integrated circuit, the same IC. That is exactly what these things are, exactly what I have here. The op amp can fit nicely in this groove between the 2 sides of breadboard. The orientation, you can see that notch on the top there corresponds to this notch on top between pins 1 and 8, that little like divot there. So, given a typical application here, we can see some labels, and this is the same kind of circuit that I have here. For our circuit, we're going to have a +3 and -3 voltage supply. You can look at the data sheet here as well to see what sort of characteristics this specific op amp has. Temperature, inset, offset, power supply. If you look down here at supply voltage, you can see VDD is around 6 volts. That is assuming that its VSS is grounded. Here, you'll notice that the absolute maximum ratings, VDD minus VSS, is 7 volts. So that means that we can put a +3.5 and a -3.5 across this as a supply, and that will be the absolute maximum rating that this device can handle. Other op amps, such as the LM741, here's another data sheet. This is a very, very common amplifier. Common op amp that is used in a ton of different applications. But for the positive supply and negative supply here, you will see that we have different ratings, absolute maximum ratings here. The supply voltage for an LM741, you can see the positive and minimum maximums can be 22 volts. So, different op amps have different characteristics. For this video, we'll be focusing on this MCP6002 and you can look it up, the data sheet for your specific application, or look up the data sheet for whichever op amp you have. Back to this mess. All right, so we have MCP6002. I just wrote out the pinout again. We have an input for non-inverting, an input A for non-inverting, an input A for inverting, that minus. The output of this op amp, VSS will be our negative voltage, and VDD will be our positive voltage supply. So how do we create this schematic? How do we create the voltages that we need? We need to use this power supply to create our negative and positive voltage output from the power supply. So one way to do this is we're going to need 4 things coming out of this power supply. And this technique can work if you do not have this specific device, but you will need to be able to tie independent power supplies to a common ground reference. So here, let's just start with ground. We are going to tie everything in this lab to the same common ground point. I'm fighting my wires over here. 1 second. All right, let's just start with ground. Here's ground. Ground's right in the middle. So if you have independent, series, and parallel, if these 2 switches are pressed in, what you want is both of them to be out for independent operation. So both of them are now out, and that means channel 4, 2, 1, and 3. Every power supply on here for our 4-channel power supply will have independent operation from each other. So then we can tie different channels to ground for the appropriate reference point. In other words, we can have everything refer to the same point, the same 0 volts, the same ground node. That way we can have a positive 3 offset for our positive rail voltage and a negative voltage referring to the same 0 volt point. Cool. So given ground, we're going to need just a ground as one of the outputs here because we want to tie our circuit to ground here. So that's what that ground is going to be. Next, let's look at what our voltages can handle here. We have channel 4 can do 8 to 15 volts. Channel 2, right here, can do 0 to 30. Channel 1, right here, can do 0 to 30. Channel 3, right here, can do 2.2 to 5.2 volts. You change this voltage up and down for channel 3 using this knob. Channel 1 goes to these 2 knobs, channel 2 goes to these 2 knobs, channel 4 goes to this voltage knob. Since we want to sweep from 0 to 3, V input, we're going to have to use either channel 1 or 2 for that because those 2 can actually go to 0 volts. So let's use channel 3 for our positive 3 volts. To do that, let's take some voltage supply. Here we go. Tie a red cable right here. That's going to be our positive voltage. And I'm going to have a cable coming out here. And then I want to tie the negative reference point to ground. So that way, our independent power supply on channel 3 is now tied to this ground node. I need to turn this on, get some numbers to look at. So output is off. I can select what is being displayed here using this switch. Channel 3 is on the bottom, channel 1 is on top. Looks like it's at 2.5. I'm going to change this knob up to 3. There we go. So now channel 3 should be outputting 3 volts, referring to this ground reference point. Next, let's do negative voltage. So we want a positive 3 here, which is good for this. Now we want a negative 3 volts over here. So let's use channel 2 for that. Move my thing over here. To get a negative supply voltage, I'm going to tie the positive output to the common ground, and then as I turn up the voltage, this will be a negative offset, a V minus or VSS for the negative supply voltage, and we're going to turn that up to 3. So positive to ground, and then negative out is going to be our line. So positive to ground, and then we want a negative output. Let's take this, negative out. There we go. So now I have this voltage here. I attached a little jumper cable to interface with the breadboard a bit easier. All right, so now we have a positive 3 volts on this one, but a channel 2 is displaying 0 volts here. That's because our voltage knob is all the way down. So let's turn that up to 3 volts. There we go. Cool. So now we have a negative 3 volts here on channel 2 and a positive 3 volts on channel 3. And a ground coming out. So then lastly, we want to sweep from 0 to 3 volts for V input. So let's use channel 1 for that. So let's change the display to channel 1. Notice we have 0 volts. That makes sense because now we have this knob all the way down. Let's take some cables. We want to tie this one also. We want to tie everything to refer to the same ground. Got a lot of cables coming out of here now. And then take the positive output point of channel 1. Here it is. And now that is going to come out, and that is going to be our 0 to 3 volts that we're going to sweep for an input. Great. Now I got all these wires hanging off here, but we should have 4 different wires that we can now attach to our breadboard circuit. Here's our chip. Here it connects to each of these 5, for breadboard again, each of the 5 holes horizontally is a single node. So if you put it right in here, you can have each of the legs of the integrated circuit connect to a bunch of different nodes. And then you can input signals or voltages or connect pins together using a breadboard like this. So if we look back at our schematic, now that we have our power supply set up, we need to set up our op-amp to perform our lab experiment. So let's try and connect this positive 3 volts first. So we said channel 3 first was going to be our positive 3 volts. So I'm going to take this and connect our positive 3 volts to the top pin there, VDD. I don't know what pin I should connect this to. There's like 8 pins here, but good thing I found the datasheet and looked up the pinout for my device here. See that VDD is the top right pin. So I look over here. I am oriented correctly. I'm going to connect this to the top right pin here. And now positive 3 volts is connected to the correct pin, VDD. Another way to do this would be to connect our positive voltage to this power bus, and then you can connect, maybe you had multiple op amps here, and I want to connect that positive voltage to multiple op amps, and they're all running on the same rail voltages, positive and negative 3 volts. I could then tie my positive voltage here, my negative voltage to the blue line, and then I can run power to this op amp chip off the power bus, as it's called. For this demo, let's just connect directly to the chip since we don't have other chips to worry about here. Yep, cool. Next, let's connect ground since we just connected power. So I have my green cable here and a green wire here, and let's connect ground. Let's use this bus as ground. So now all of these lines are connected to ground. And then we'll need to connect ground to our different circuits here. So we have ground, and that's connected to our input voltage, which we already did that here. Our red voltage here is our input voltage, and we have channel 1 tied to ground already, so we're good there. Input voltage should be connected to our non-inverting input. That'll be V in op amp A, non-inverting positive, plus symbol. So let's take this. Pin 1, 2, 3, 4, 5, 6, 7, 8. It is a counterclockwise counting for pin numbers. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3. Pin 3. 1, 2, 3. Oh, there it is. That is connected. Okay. Now, what else do we have in the schematic? So we connected positive 3. We connected V into our non-inverting input. Let's connect. We have ground connected here. We haven't connected it to our circuit yet. So what is grounded? Looks like our input was grounded already through our power supply, but we need to connect this negative input to a resistor across here. Use a resistor to connect ground to our inverting input. So I got some resistors here I pulled out previously. Let's take that. Our inverting input looks like pin 2. So now I've got pin 2 tied to ground. Let's get our negative voltage connected now. So remember, our negative voltage was channel 2, and we set this negative line out. Here we go. Let's look at our pinout. I need a negative voltage on VSS here, so I'm going to connect this to VSS. All right. What else do we need? We need a resistor 1 feeding output back into the inverting input. So this is a feedback resistor. This will be R1. So let's set up R1. What is our output? So we look here to our pinout. Where is our output? Our output is pin 1 we're using the left op amp. And our negative input for the op amp A, our inverting input, would be the next pin down. So pin 1 to pin 2. Take a resistor. Pin 1 to pin 2. There we go. So you can see I connected a resistor from the output of pin 1 to the input of pin 2. All right, so now we have power rails, positive and negative. We have an input in orange. We have 2 resistors that are one's connected to ground, green, and then we have our output connected to our negative input. Lastly, we have these capacitors here. Often we have filtering capacitors, which you might see on a schematic here, bypass capacitor connections. This is a way to filter out high-frequency noise in your supply. Let's say you had a very high-frequency noise that was introduced into your constant 3 volts and constant negative 3 volt inputs. It'll be bad if you have a very fast transition from on to off and then back on again. This would be like a fluctuation in the power, like when the lights in your house start flickering. This is the same kind of thing. What we want to do is filter out the high frequency noise in our circuit to give a cleaner input power to our op amp circuitry. That will make things operate a bit easier. So to do that, for the supply voltages, on the same node as the supply input for the positive and negative supply voltages, it looks like we connect a capacitor to ground, C1. So I've got 2 caps here. Let's connect from our positive input I'm going to connect the same node for positive input. Come on, get in there. There we go. To a node, and then we need to connect that node to ground. Let me get another cable. There we go. So now I have on my positive 3 volts in VDD, I connect that same node through a capacitor to ground. Through a capacitor, and then I have a jumper wire here to ground. Same thing goes for our negative 3 volts. I might just connect this directly to ground. Let me move this over a bit. Same node. Opens up a place for me to connect directly to ground. There we go. So on the same node as our negative 3 volt input, I have this capacitor through the capacitor to our same ground node, as you can see here. Great. All right, so that should keep our power supply. It's pretty good already. Now we have additional capacitance to block out the high frequency noise from interfering with our circuit. So also, we would need to look at the output, because what we want to see is the output here. We're going to sweep the input from 0 to 3 volts, and then we're going to look at the output voltage. We're going to measure it with our multimeter here to see what we get. So our output would be pin 1. Let's take a jumper wire here just to see what's going on. And I'm going to tie that to just a node over here so I can poke it with the multimeter. And let's see, looks like we have all of our wires connected. Looks like we have a bunch of things set up to create our non-inverting amplifier. So let's think about what we should expect to see. A non-inverting amplifier is defined because we have an input voltage tied to our non-inverting inputs. We have maximum supply voltage of positive 3 and a minimum of negative 3. That means whatever output voltage we have here, the maximum is going to be positive 3 and the minimum is going to be negative 3, no matter how much gain we give the circuit. So for an amplifier, we'll take an input voltage, let's say 1 volt, and multiply it and amplify it by the gain here. We're going to multiply by the gain. So the gain is defined as the output to the input relationship. And that is defined as VO divided by VN equals 1 plus R1 divided by R2. So the ratio between the R1, the feedback resistor, and R2 defines how much gain that we have on this amplifier circuit. So if they're both the same value, we'll have a gain of 2, expectedly. 1 kilo ohm to 1 kilo ohm gets you 1. 1 plus 1 equals 2. Given an input of 1 volts, Vn times the gain equals our output voltage. So if we have 1 volt times the gain of 2, we'll have a 2 volt output. If we have an input voltage of 3 volts, then we'll have Vn of 3 times a gain of 2, and that should equal an output voltage of 6 volts. However, we have a maximum positive input, maximum VDD is going to be positive 3. Our minimum will be negative 3 volts. Therefore, any output voltage that that is above our positive supply here will be clipped or limited to positive 3 volts. The terminology here would be clipped, limited, saturation. You hit the ceiling, you hit the rail, you can't go higher than your supply voltage here. So let's give this a test. So I have this off currently. I'm going to turn this on. And I notice that we have 0 amps, nothing's happening. That's good. If you see voltage, so now we go to channel 1 at 0, also good. If you see a lot of currents here, like 0.5, 0.4, something like that, that would indicate that something's going wrong in the circuit, or maybe your op-amp chip is blown, possibly. But this is looking good so far. So, positive 3, negative 3 volts. Let's go to channel 1, and we have 0 volts in. 0 times 2 should get us 0 volts on the output. Alright, I've swapped probes. And so let's measure the output voltage to see what we get. So this was our jumper cable that we used for output. And I've tied some cables to our multimeter. Our input is 0. And it looks like our output is currently 0.009 volts. So pretty much negative, even that. So pretty much 0. So let's try and increase the voltage now of our input channel 1. With a gain of 2, I would expect to see twice the input on the output. So let's say an input of 0.5. Looks like 1.1 volts. Looking pretty good. Let's go input of 1. Yeah, 1.1. 2.2, almost. 2.19. Alright, and let's test clipping. Remember, channel 3. It's a positive 3 volts. So if we have an input of 0.5, 1.5, should get a 2.96, so almost 3 volts on the output. Now let's do an input voltage of 2 volts. I can barely get that. There we go, 2 volts. Still 3.005. Let's go up to 3 volts. And look, we still get an output voltage of 3 volts. So we can see that we are now hitting the ceiling, or hitting the positive voltage supply of our op-amp. Go back down. I'm going to turn the knob down to 0. I go back down to 0. I'm going to turn it up a bit. And it goes up to 3 volts and then stays there. So we have validated that we have a gain of 2 and that we are hitting the top voltage supply. Cool.